So I'm going to start off today, put that on, there we go, with space exploration. Okay, that's what I'm going to talk to you a bit about today. Okay, so I didn't know the backgrounds of all of you, so I sort of arbitrarily come up with a bit of backstory for you for space exploration. Okay, so many years ago, okay, Middle Ages, we had the belief that the Earth was flat. Okay, this is hopefully not news to anybody. Good. Okay, I don't know if there was dragons underneath it, but the idea was if you went to the edge of the world, you'd fall off. Okay, and people used to explore and try and get to as far as way on the map as they possibly could. Okay, and see what were the ends of the Earth. Okay, that was what people used to do. Okay, now I say used to do, but I'll tell you a bit of a story. I was in the gym about 2-3 weeks ago when I was planning this lecture, and one of the guys in there told me about a new video he'd seen. Okay, and he wanted me to watch this video. He was very keen on me watching this video because I'm a scientist. So, okay. So, I typed in flat Earth, the biggest lie of all. This is not a plug for the show. I would not recommend watching it. Okay, and I came up with this YouTube video. And in this YouTube video, it told me all about how I was wrong. Okay, because I believe the Earth is not flat. Okay, but they believe it is. Okay, and it was quite intriguing. As a scientist watching this, I can see how some people might be swayed in certain arguments. But the long and short of it is, it's not true. Okay, so what they said is the Earth's flat like this. Okay, and you had the sun, and you had the moon, and they circle this flat Earth. Okay, and as a lecturer, I'm inherently biased, and I'm telling my lies to you because I want to convince you of the fake truth that keeps you imprisoned. Okay, don't know how. Okay, and they had some, there's some good arguments here, I suppose. They said, okay, if you're in Sydney, okay, over here, how come you've got to fly to Dubai to fly to Johannesburg? Okay, that makes no sense on a map. You're flying up north to Dubai and then down to Johannesburg. But if you look on this flat Earth map, it's almost a straight line. Yeah? You see? You could, of course, make the counter-argument that if I wanted to fly back home to England, I just fly straight over here, and it should take me about 10 hours. It takes 24 hours because you can't do that, because the Earth's round and it doesn't work like this, okay? Plenty of other arguments about horizons and all this stuff, okay? But if you are interested, please do watch it. It's quite comical, some of the arguments, okay? But just remember, it's not true, okay? The Earth is not flat. Yes? Good, okay. So hopefully you know the Earth's round, okay? It's a sphere, give or take, okay? And we live on it, okay? And we're currently in Australia, which will come up down there. There we go, cool. Okay, so we're in this. We're not in this world. There's no flying turtle going through space or anything like that, okay, remember? Nice round circle. Okay, this reminds me of this quote from Mark Twain here, which I do thoroughly believe in. So never ever argue with a stupid person because they will drag you down to their level and they will beat you with experience. Okay? Use your intelligence. Okay? And I would say that through the entire course. Remember, try and think about some of the science, try and get an understanding of what's going on. Okay? And that will really help with some of the explanations and some of the tasks we've got later. All right. Okay, so this is the solar system. Okay, and we, Earth, is around there, okay. Hopefully you've got an inner set of core planets, and they're mostly made out of rocks, okay, and rock planets. You then have the asteroid belt, okay, and then going further away, you have the gas giants, okay, and that's sort of how our solar system is, okay. We have the sun in the middle, and we go around the sun, yes, good, okay. And Pluto's got a strange orbit and is no longer classified as a planet, which I was very sad to hear when that happened. Okay, so that's where we are. So if we look a bit closer to home, okay, so we've explored most of Earth, so now we need to explore a bit further away. Okay, so we're going to now go closest object to us we could possibly go to after the Earth, okay, is this thing here, the moon. Okay, now that is quite a way away. Okay, if you were to drive a car, okay, at New South Wales speed limits, is about 110 kilometres per hour, it would take you about 146 days to drive there. Okay. Now, I know Australia is big, and you might be used to travelling long distances, but 146 days in a car is a long, long time. Okay. So what you need to appreciate is we need to go a lot quicker to get there in a reasonable time frame. Okay. So what you use is a rocket. Okay. So what we have here is the Saturn V rocket, and I wanted to show you this because it'll link to the film in a bit and you'll understand a few more of the acronyms that we'll use, okay? So in the top bit up here, okay, of the Saturn rocket, we have the Apollo spacecraft, okay? So inside the cone here, we have the lunar module, okay, which is the bit that lands on the moon, okay? Often abbreviated to LM, okay, the lunar module. That's connected up here to the service module, okay, which is where most of the habitat for the astronauts were when they went to the moon. Okay? And what happens is this has obviously got a lot of thrust, a lot of energy. It takes off. Okay? It has enough force and enough thrust to leave our atmosphere. Okay? When it gets up to a certain stage, part of the rocket falls off, okay, because you've used the fuel up. It's just dead weight, so you want to get rid of the weight. The next stage burns, gets you into the rest of the atmosphere, into the outer atmosphere, into orbit, and then what happens then is the final bit separates and you're just left with this bit at the top here. Okay. When you're then in space, what you actually have to do is connect this bit here, okay, because this is like a little service bit where the astronauts live with an engine. You have to connect this bit at the top here to this bit here. So you've got to separate, turn around, and reattach. Okay, that's quite a dangerous manoeuvre. Once that's happened, then you can continue on the journey. Okay, so that's how these Apollo missions work. All right. Hopefully you're also aware that when we leave the protective atmosphere, okay, what we have is solar radiation. So the sun emits huge amounts, okay, of particles, okay, and radiation, and they go towards the Earth. Now, fortunately, the Earth has a magnetic core, okay, and that creates a magnetic field around our Earth, which protects us from these solar winds, okay. So they're deflected by the magnetic field. However, if you leave the atmosphere, okay, and you go into space, you're leaving the Earth's magnetic field, okay? So there's a huge amount of solar radiation that's going to hit you as you go towards the moon, okay? There's also something called the Van Allen bands, which are around here and here, which just because of the way that the solar radiation moves, you actually get an accumulation of extra radiation in bands around the Earth, okay? Doesn't affect us, okay? But it affects things like satellites. You need to make sure that when you launch satellites into orbit, you're either close enough so you're not in the band there, or you're far enough away so you're not in the huge amount of radiation there. Okay, so that's one of the considerations about where you put a satellite, for example, its distance from Earth. If you're going to go to the moon, you're going to have to cross through these Van Allen bands, okay? So you're going to have some form of radiation safety. You're going to have some form of shielding on your spacecraft, okay? Otherwise, you're going to have a huge dose of radiation. You're all going to get cancer and die, okay? Depends on the amount. You could be within a couple of hours, okay? So it could be a lot of radiation there, so you have to be really careful from the build up here. So ideally you want to move around or pass through as quickly as possible. Okay. So, differences between the Earth and Moon, they are both spheres as far as I'm concerned. Okay. On the Earth we have lots of water, we have an atmosphere, we breathe oxygen. Okay. The Moon, these are not to scale in case you wondered. Okay. No atmosphere. Okay, it's smaller. Okay, it has less gravity. Okay, because gravity is an effect of mass. Okay, so the bigger something is, the more gravitational pull it has. The Moon's smaller than the Earth, has less mass as well. That means that there's less gravity on the Moon. Okay, because there's less gravity, it couldn't hold an atmosphere if it wanted to. So there is no atmosphere on the Moon. Okay, it is just a rock in space. Okay, going around us. Okay, simple as that. And as you can see here, this is not, I think this is Apollo 15, I think, or 16, because of the lunar module, the little craft here. Spacesuit, okay? That spacesuit there has got lots of insulation to keep the heat in, because remember, space is very cold, okay? So he has to keep the heat of his body in, otherwise he'll freeze to death. There'll also be some protection from solar radiation in that suit as well. Believe it or not, tin foil was used quite a lot in spacecraft design in the early days. Hey, if it works, I'm not going to complain. Okay. Which is what this here, this lagging here, is basically a bit of thermal lagging with some things around it. Yes?
Is the Moon
Okay, is the moon circular because of its form? Basically, when it formed as a sphere. As simple as that. No, in the same way that when planets form after a supernova, it's just the rocks and all the different material coming together, and that ends up roughly as a sphere. Okay, I believe there's some talk of old volcanic plates and things like that might have set, but if there were volcanic activity, that was a long time ago when we were first forming the moon. Nothing like that anymore. Okay? Yes?
Any particular reasons why they use tin foils for spacecraft?
The reason why they use the tin foil here was because it's cheap and it works. A story for you would be, obviously there's no gravity in space. Okay? Or there's very little gravity because you're far away from any mass or body. So, NASA spent millions and millions of dollars creating a writing implement, you guys called a pen, okay, that would work in zero gravity, all right? The Russians used a pencil, which doesn't need to have gravity to work, okay? It just creates pressure, okay? So the moral of that story is don't spend millions and millions of dollars when something really simple will do. Yeah, that's the reason. As long as it's thick enough, it works, it's cheap, hey, let's use the stuff, okay? But yes, this is the service module, so this lunar module, so this landed on the moon. The extra bit that was on the top had still been in orbit going around, okay? And then the idea was then this lifts off, it'll reconnect with the service module and they can go back to Earth, okay? Yeah, you've got the lagging installation there, the nice American flag, of course. And this is actually a lunar rover, which only appeared in later missions. It didn't appear in the early missions, and this was just so they could drive around a bit on the moon, okay, and go and explore a bit further than if you had to walk, okay? They're still there, okay? So if you ever go to the moon, there will still be the little go-karts lying around, okay? Because they don't take anything back if you don't need to, okay? So mass-wise, you leave everything behind that you have to, okay? Obviously not shown here is the fact that it's low gravity, so if people try and walk, it's like bouncing around. I'm sure you've seen plenty of video clips and stuff like that of like Neil Armstrong bouncing around on the moon and stuff like that, okay? So that's the considerations you need to make. That is a general time frame of what would happen in a mission. Okay, I'll very quickly talk you through it just so you're a bit more familiar. So you'd leave Earth, okay, here. You'd then, hang on, I'm leaving Earth here. Sorry, my apologies. Leaving Earth here, going up, okay. Once you get a certain distance away, or a certain distance around, what happens there is that's the separation of the command module and the service module, separating from the cone, turning back round and reattaching, okay? So that's what's happening at that point there. Once that happens, then what you do is you head towards the moon, and what this here is it's using sort of the Earth's gravity to help accelerate and help keep you in motion, okay? A quick little burst of thrust allows you to go towards the moon. Then when you're at the moon, what ideally would happen is you'd do a few orbits, okay? So you enter its orbit. Then you're just using the moon's gravity, just to keep you where you are. You're not having to constantly use thrust or anything like that, or try and do it in one shot. The idea then is that the lunar module will detach, go down towards the moon, land on the moon, collect some samples. You might do a few experiments or a few tests, but it is, over 70s, there's not too much to do. And then you're going to get back into the module, you're going to take back off, reconnect with the service module in space, give a quick burst at the right point to just accelerate just enough to leave the orbit, and then use that to slingshot back towards Earth, okay? And then re-enter, okay? And that's a standard lunar mission would be, okay? So, why did I put that there? That was to remind me of something, I can't remember. Oh, that was right, yeah, okay. So, the first Apollo mission that was successful in terms of landing on the moon was Apollo 11. Okay, you should all be familiar with that, hopefully. That's something I learned that years and years ago. Okay, and that had Neil Armstrong, Buzz Aldrin, and Michael Collins, the forgotten astronaut. Okay, so what happens here is there's always 3 people on an Apollo mission. There's always 3 people that go into space. So you have a mission commander, who is Neil Armstrong. You have a pilot for the lunar module, which is what lands on the moon, and that was Buzz Aldrin. And then you have a pilot for the command module, okay, which here was Michael Collins. Now, unfortunately, that means that the person who's on that command module doesn't get to land on the moon. Okay, they have to stay in space and orbit the moon. Okay, that means out of every 3 people that go to the moon, only 2 get to land on it, okay, in the old Apollo missions. Now, there were 6 successful Apollo missions, okay? Now, my maths holds out just about on this one. 6 times 2 is 12. So, 12 people have set foot on the moon, okay? Ever. That's it, okay? Now, there is talk of going back to the moon, and then that number will hopefully increase. But at the moment, yeah, only 12 people have ever set foot on the moon. Okay. I said 6 successful missions, okay? So what this here is, okay, this film that we're going to put on after I finish my lecture, Apollo 13, okay, is about one of the missions that didn't go quite right, okay? Now, I don't know how well known the film is in terms of if you've all seen it. I happen to think that most people should have seen all the films on this course, but hey, might not be true, okay? So it's about one of the missions of Apollo 13. There's also this film that I could have put on for you, okay, Apollo 18. Now, in the same way that the Earth is not flat, and hence the Earth isn't flat, and hence it's round, okay, and people don't know everything. This film here, Apollo 18, is also not a true story. Okay, so Apollo 13 is a true story, or based on a true story. Apollo 18 is not a true story. Okay, there was no Apollo 18. Okay, despite the shoddy video and camera work in the film. Okay, it's not a real life story at all in any way, shape, or form. Okay, in fact, people actually thought this was true. Okay, when it came out. I don't know. I'm not even going to try and work out why it was. Okay. Cool. So, we're going to watch the film about how you get from Earth to the moon. But in terms of space exploration, okay, we've done that now. Okay, we've been to the moon, as long as you don't believe the conspiracy theorists. Okay, where do we go next? Okay, because that's what exploration's about. Okay, you don't stop exploring just because you've been to one place. You keep going as far as you can. Okay, you need to discover as much as possible. Okay, so options. Okay, from here, Earth. Well, the nearest things are either Venus or Mars. Okay, they're the next 2 sort of options. They're the next 2 in terms of distance away from us. Okay, Mercury's not too much further, so you could go to Mercury potentially. Okay, Ceres is a very, 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 very rare, very large asteroid in the asteroid belt. Okay, now unlike in films and TV shows, the asteroid belt is not a constant moving big collection of rocks all the time. Okay, they're pretty stationary. There's quite a lot of gap and distance between them, so it's not as difficult as you might imagine to get to an asteroid belt and survive. Okay, if you wanted to go to Jupiter, Saturn, Uranus, Neptune, okay, or even passing comets that might happen, okay, you've got to think about distance involved. Okay, these are quite far away. You've also got to think about landing on them. Okay, I mentioned before these are called the gas giants. That means they're mostly made out of gas. Kind of hard to land on gas. Okay, so they're probably not going to land on those anytime soon. Problem with comets, I suppose, is you've got to time it just right, okay, because they're going huge distances from the sun and coming back, and you've got to time the mission just right to be able to catch it as it's going past. And obviously you can't stay there for very long because otherwise it's going to go too far and go back out away from the solar system, and then you're stuck on a comet. Okay. So yeah, so I'm going to look at the inner planets now. Okay, I'm going to see which ones we could go to. Okay. So again, distance not to scale. Mercury. Okay. The side that faces the sun is very, very hot. Okay, you're talking hundreds of degrees. Okay, very, very hot. But the side that faces away is very cold. Okay, so you've got to really think about hot and cold, a quick change. Okay, you're also going right towards the sun. Okay, which I'm pretty sure is probably not recommended. The reason why it gets very hot, very cold is there's no atmosphere. Okay, so because the solar radiation has completely burnt off the atmosphere that ever was there, if there ever was one. Okay, it means that you're going to have some hard problems there, some hard times. Okay. Venus, okay, is always hot. Venus is an example of the greenhouse effect dialed up to 11. Okay, so what happened here is loads of CO2. Okay, and that's heated up the planet. There is an atmosphere, but because it's heated it up in the way that our planet is heating up, allegedly, with more and more CO2 that's being produced, okay, there it's ridiculous amounts of heat, okay? I think you're talking several hundred degrees, you're talking about huge amounts of pressure as well, and the atmosphere also has things like acid in it, Okay, so your space suits, for example, if you landed with a metal spacesuit or some form of metal on it, it would be corroded and start to react as soon as you land there. Okay, so it's probably not the best idea to land a metal spaceship on Venus. Okay, that's why the probes don't last too long. Earth, we've already been there. Okay, that's just for comparison. Mars is the next one. Okay, so cold to very cold, has a thin atmosphere. Okay, in terms of safety or in terms of what's most feasible, I suppose Mars is probably the best option next. Okay, just due to the high CO2 and acid from that, the fact that that's pretty close to the sun and is ridiculously hot. Mars is reasonably far enough away. Okay, it's going to be cold, have a small atmosphere, but at least it's not right next to the sun. Okay, so that's one of the options. Okay, so there's been plenty of films about this, because remember, this is science in the cinema. Okay, so does anyone know what film this is? It has a really obvious name. Mission to Mars, excellent. It is indeed Mission to Mars, yes. Okay, I would not recommend watching it. It's not particularly good. There's also another one which is very, very similar, which the name escapes me, which is also equally terrible, but it was made at a similar time. I think this was made in the mid to late 90s. Not a great time for some films. Okay, so yeah, the journey to Mars, what would happen? Okay, so this is obviously being developed and in the planning stages at the moment. Okay, so for example, the SpaceX program with Musk and all those kind of people, they're all putting money towards this. And no one's 100% quite sure the exact mission outline yet, but there's talk of developing a new spaceship, okay, a new craft to get to Mars, okay, because the Apollo one wouldn't really work. It's too small, not enough resources, okay. Also, I don't think it can actually land and take off on Mars because Mars has got a higher amount of gravity, so you'd need extra thrust, you'd need a different craft. There's also talk about different kind of propulsion systems. There's also talk about making bases on the moon and all sorts of stuff like this. So there's lots of things in discussion still about how we're going to get there. Okay, but the technology is being developed and they are working on this kind of thing. Okay, so yeah, a moon base. This is not some sci-fi drama anymore. You know, we could actually have a permanent base on the moon. Okay, and this could have all sorts of implications and problems, mostly because I believe the Russians were trying to develop one in the Cold War. That was the idea of getting to the moon. You put some nuclear missiles on the moon, and then you can aim at Earth whenever you want, and you don't have to worry about being attacked because you can't really destroy a moon base because it's on the moon. Okay, so that was one of the problems originally. But they talk about this new craft, the Orion spacecraft. Okay, so this is the kind of a new concept that's being tested, I think this year actually, end of this year, start next year. And they're actually going to use this to dock with the International Space Station. They're going to do some test flights. Okay, and ideally, this will probably be what people travel to Mars in, or something very similar to this, maybe with an extra module or two on board, but this is what they're doing. Okay. There's also people doing psychological tests. I don't know if you heard about the deserts, and I think there's someone in Hawaii, I think it was, where people pretended to be on Mars. So they had some astronauts locked in a, in a little tent thing, and they had to do all the procedures. They had to go out and collect rocks. You know, people have also been in, I think, was it in Russia or something? They had to spend time inside a metal cylinder that mocked up a spacecraft for, a year or so just to simulate the distances they'd have to travel and all this kind of stuff. So there's all sorts of kind of experiments going on at the moment to see if it is even viable, for a human to survive that long in space. Okay, that kind of stuff. Okay, so yeah, that's the Orion spacecraft compared to the Apollo spacecraft. In terms of size, they're not too different. Okay. But they are being developed, all the new technologies and new facilities you might need on board. Okay. When they do get to Mars as well, okay, you're going to have to think about how long you spend there. So people are talking about making permanent bases, but because of the atmosphere being quite thin, and it's like a magnetic core, you get a lot of solar radiation hitting Mars. So they're talking about burying modules under the Earth in Mars. I use Earth for soil as opposed to Earth being the planet. Underneath the soil there. The idea being that the solar radiation will be absorbed by the soil, and hence your habitat underneath would be safe. Okay, so that's one of the considerations people are making. Also, if you're burying it into the soil, you have to think about how heat loss might occur and things like that, and how you could insulate. Okay, so Earth's not too bad of an insulator at times, so that's why they might be thinking about doing that. They're also talking about growing vegetation on Mars to set up a permanent colony. the ultimate long-term goal. So if you don't want to be constantly sending oxygen there, you don't want to be constantly sending food there, you want it to be able to be made there, okay? So Mars has got loads of CO2 in the atmosphere, although it's a thin atmosphere, okay? So the idea being that there'd be enough CO2 to, have some photosynthesis occur. You might have to compress the CO2, but you'd at least have some, okay? And there would be sunlight, but how that'd interact with plant species that are, evolved on Earth, not too sure, okay? So there's going to have to be a huge amount of work involved in that. The accompanying film to Apollo 13 in this series is The Martian, okay, with Matt Damon. So that's available online. Please do watch it. There's a quiz associated with it as well. And to be honest with you, that is not too far off what might happen in terms of scientific, accomplishments and some of the considerations. It's not outlandish that what he does might happen or might work. Okay, so the science in that is actually pretty accurate and pretty true. Okay. Of course, it's not a true story. Again, people thought it was. People actually thought that Matt Damon was the first person on Mars. I know. I don't know where this stuff comes from. Okay, so Mars is the next step. And I always love the Buzz Aldrin, get your ass to Mars, which reminds me of some of the films. Okay, so I don't believe there's wildlife on Mars, okay, but some people do. So this is a film that was released, I think 2009, I think it was. Anyone know what this one is?
John Carter on Mars.
It is John Carter on Mars, yes, Disney, well done Disney. I don't believe there's these giant monsters on Mars. Don't get me started on the atmosphere or any of the gravity or anything like that in this film. It's complete fantasy, okay? Plus you can tell it's CGI, can't you? It's not real, okay? Of course, we've got one of my favourite movies about Mars, okay, which is Total Recall. And it's only, of course, because of this guy, okay, Arnold Schwarzenegger. It's I love Arnie. Again, I could have put this on as part of the course, but I'm not too sure there's too much science involved in it. Some bits there are, but it gets a bit abstract. So yeah, there's plenty of films about Mars and stuff like that. Okay. So in terms of distance, this is what we've been talking about, okay? So Earth's there, the moon's pretty much next to it, Mars is there, okay? And that's going to take us a long time to get to, okay? What happens if we want to go to Jupiter, Saturn, Uranus, Neptune, Pluto? Okay, that's just in our solar system, okay? It's all going to take time, okay? The further something is away, the more time it's going to take us to get there, okay? Now, there's been several other projects in terms of how to get faster, okay? So at the moment, this was a project called Daedalus, which was in the 70s, I believe it was. And the idea was this was a nuclear-powered spaceship. The idea being you'd have a nuclear reactor and you'd spray liquid hydrogen into it to create thrust, okay? Works, does work. Slight problem, you don't really want to launch a nuclear reactor into space. If it blows up and then spreads nuclear waste all around the planet, probably bad, okay? So that was scrapped, unfortunately, but I think it looked cool, okay? And the other idea is these solar sails. So you could have a spacecraft, you could deploy a sail, it would catch the solar radiation and hence accelerate you, okay? No matter what any of these technologies come up with though, okay, there's one crucial problem, all right? And that is the fact that if you have mass, okay, essentially you can't go faster than the speed of light, okay? You can approach the speed of light, but it takes a huge amount of energy. This is the E = mc squared, special relativity, Einstein kind of stuff, okay? If you want to get to the speed of light, you have to have a huge amount of energy, and that gets exponential the more mass you have, okay? In terms of distances, if you were, let's say, to travel at the speed of light, okay, so let's say we could somehow get to the speed of light or very, very close to it, okay? Right, so Earth to the Sun's about 8.5 minutes, okay? Sun to Pluto, so if we've got to go to Pluto, it'd probably take us about 5-6 hours. That'd be pretty good, that's not too bad, okay? But if we ever wanted to leave our solar system and go to another solar system, okay, the nearest star to us, okay, is about 4.5 years. Okay, that's how long it'd take us if we could get to the speed of light. And then if we get there, you'd have to send a message back home saying you got there, that message travels at the speed of light. Hence, it'd take another 4 years before you knew if the spaceship got there, okay? And then if they wanted to come back, or you wanted to do another mission, keep adding years and years and years and years and years, okay? And that's just to this closest star. What happens if you want to go across the galaxy, okay? What happens if you want to go to another galaxy, okay? It's impossible in our sort of time frame in our lives, okay? And that's what we think, okay? So, some options, okay, what we could do is create what's called a generation ship, okay? The idea being that the spaceship, you live on it, okay? You live on it, you have a family, you die, your family continues the mission, okay? They die, their family continues the mission. Eventually, the human race gets somewhere else, okay? That's one idea of a generation ship. Not too appealing to me. If there was, the mission to Mars, people are saying volunteer, yeah, go to Mars. No, I'm going to stay here. I don't want to waste my life and go to a planet and die. Okay, I'd rather just stay here. It's much nicer, right? Okay, so generation ship's one idea, all right? There's actually a sci-fi TV series about this called Ascension, which is a limited-run TV show. It's about 6 episodes long. If you actually can find it, I'm not saying how, you might find this TV show. I actually would recommend watching it. It's actually pretty decent. If you like Battlestar Galactica or anything to do with space exploration and things like that, it's actually a pretty well-made show, and it's actually quite clever. So I quite enjoyed this one. Okay, that wasn't too bad. Okay, but what I want is this. Okay, I want spaceship. Get there. Okay, I'm impatient. I don't like waiting around. Okay, so. Obviously, this is from Star Wars, in case you're not familiar. Okay. So the idea being, out of nowhere, you engage some magical, mystical drive and catapult it across the universe, okay? Or the galaxy in this case, all right? So how might we do this, okay? Okay. So you could have here, okay, some kind of wormhole. Now this can be a kind of a weird, abstract idea for you. Depends upon how familiar you are with space-time, how familiar you are with different dimensions that you don't live in, okay? Because this gets my head sometimes, okay? The idea being that you could fold space. So if you imagine you make a magical rip in the fabric of space and time, it opens up somewhere else, you could travel straight through one side to the other side, okay? So imagine a piece of paper on my hands, okay? Distance between my hands is relatively large. If I could somehow bend and make them touch, you could go straight from one hand to the other without having to cover huge distance of the body, okay? It's kind of hard to imagine how it might happen, especially if you're not too familiar with spatial awareness and stuff like that. Believe me, it gets me, okay? That's one option, okay? Creating one of these bridges and going straight through, okay, to the other side. That would mean you'd be able to cover, in theory, that entire distance, which could be many, many light years in a matter of seconds, okay? Might take a few minutes. I don't know how long it takes to get through there, but put it this way, it cut down time tremendously. Okay, that's one option. Another option. Okay, one of these. Okay, that's a model. Okay, it's not real. Okay, the idea behind the Star Trek warp drive, okay, is actually less outlandish than Star Wars, which involves a alternative dimension where you somehow travel faster. Okay, I don't understand that one. And the idea of warping would be to warp the space in front of you and behind you in such a way that if you were in a bubble, you'd travel along, okay, and ride the ripple. Sort of like riding a wave, okay? Doesn't actually take you any energy to surf, okay, apart from standing there, but the difference in the energy at one side and the other, the gravity, because you're at different heights, makes you constantly go forwards, okay? That's the idea of what a warp drive would do. You'd create a different or an imbalance in the space-time before and afterwards, and you would exist in normal space-time going really quickly that way, okay? So the spaceship technically wouldn't move very quickly, but in relative terms it would, okay? I put this up, I was just like, what the heck is this? So yeah, there's whole fan pages dedicated to this and what all these numbers mean, and warp factors 9 and 10 and how quick they all go. I was actually fascinated by this. I was like going, what? Really? Okay, right. Oh, it took me that long to get to the Klingon Empire. Okay, right, okay, never mind. So yeah, there's a lot of stuff about this. And the idea of a warp drive is much more realistic than a wormhole drive at the moment. Okay, so warp drive potentially could one day happen. I don't know, probably not in my lifetime. Okay. Of course, you may ask, why do we care? Okay, so is space travel worth it? Is it even worth going to space? All right, because I've said you're probably going to die on the trip. Okay. Well, because of space travel, because we invest this money, I say we, I've obviously invested nothing, into space travel, especially the Apollo program, it created microcomputers, okay? It enables our research into technology, computers, electronic devices, okay, to accelerate at huge rates, okay, because of the money that's pumped in. In the same way that the Formula One, the money that's put into that by the companies benefits us on the street because of enhanced braking, enhanced safety features, okay? It's not a direct link, okay, but it's the money that we spend into all these new technologies does filter down to us, okay? So on Earth, if you didn't choose to leave, okay, we had water purification systems, okay? We've had car phones, you've had all the different electronic chips in your pocket, yes, your phone. Your mobile phone contains more processing power than the entire Apollo space program, okay? So that little device in your pocket with the touch screen has more computer power than all the NASA had when they sent people to the moon, okay? So appreciate the fact that that's how powerful your phone is in comparison to, 1970s technology, or 60s at least anyway. We've had enhanced TV images, satellites, satellite communication. You can talk to people on the other side of the world either via the internet or via satellite communications. All these kind of things are all benefited from space exploration. Okay, so personally, I think it's something that we should continue to do. Okay, and I believe we should put money towards it. Whether or not I'm going to be involved and actually end up going to Mars is a completely different story. Okay, that's where we're up to.